All right, well, hello everyone, and welcome to our Exam 1 review session video. So in this video, we are going to review all the DC circuit tools that we covered in lectures 1 through 10, and then we will do some practice problems. So please use this video to help you prepare for the exam. So as we go through today's video, I encourage you to make note of the topics that you want to review further. I also highly recommend that you study as much as possible by doing practice problems. So I encourage you to skip around in this video as much as you need in order to focus on the topics most important for your review. And I especially recommend you consider pausing the video and attempting the practice problems yourself before watching me go through the solution. That way you'll be able to get additional practice as you prepare for the exam. All right, so as you prepare for the exam, please refer to the topics in our study guide for a detailed list of what you should know in preparation for this exam. In today's video, we will first start by reviewing the topics in our study guide. So we'll briefly go through each of these topics and review some of the key things to remember for each topic. In the second part of our video, we'll do some practice problems. So please skip ahead or pause and rewind as much as you need in order to prepare yourself for our exam. Finally, before we jump in to the review session, I would like to remind you about my biggest recommendation about how to prepare for exams in circuits class and engineering class in general. My biggest recommendation is to study by doing problems. Please do not fall into the trap of studying by reading, watching videos, or memorizing. That will not prepare you to solve actual circuits problems on the exam. So please, as much as possible, study by doing practice problems by yourself. Put pencil to paper and verify that you can use all the different tools we've learned. By practicing problems, you're going to build your intuition, you'll get comfortable with our tools, and you'll improve your problem-solving skills. So please use the videos we've covered, the practice problems here, and additional practice problems in our homework and book to help you prepare for the exam. It's especially helpful to pretend you are actually taking the exam when doing practice problems, and that way you can check, were you able to solve a problem in 10 to 15 minutes? And if not, that might be something you want to ask a question about or review further. And remember, I'm more than happy to help answer questions as we approach the exam time. So with that in mind, let's go ahead and go through each of our study guide topics. So we'll review each item in our study guide, and then we will move on to the practice problems. So let's start with our first item, questions of the day. So I guarantee that at least one question that we covered at the beginning of class, so remember those questions towards the beginning of the video, I guarantee that at least one of those questions will reappear on the exam in some form. So reviewing the questions and examples from the beginning of lecture is a really good idea. Guarantee that one of those problems will reappear on the exam. Next item, electrical units and quantities. You'll remember in our first couple lectures, we talked about the basic quantities of electronics. We talked about current and charge. We talked about power, energy, voltage, current, all those quantities that we use in our circuits. We also talked about how current is the time derivative of charge and the derivative integral relationships. We also learned passive convention. and learned about how to avoid unit conversion errors. Please make sure that you are comfortable with each of these topics. And remember, you're welcome to review our Lecture 1 and 2 videos if you need a refresher. Let's just briefly review a couple key points. First is charge and current. Please remember, if we know our charge Q, we can take the time derivative to find current. Similarly, if we know our current, we can find charge by integrating over time. This is not math class, so I'm not going to expect you to do hideous integrals. But as I mentioned in our Lecture 1 and 2 videos, I do expect that you know how to integrate things like exponents and polynomial expressions. So if you're rusty on integrals and derivatives, please make sure that you review the lecture materials. We also learned the passive convention. And remember, to satisfy passive convention, current must enter the positive voltage terminal. If this passive convention is satisfied, then we say that positive power means we are receiving or absorbing power in that circuit element, and a negative power would mean that we are releasing or supplying power. I'm personally a big fan of the water wheel analogy. So again, this is just something silly I made up. This is not an actual official name. But if you're ever not sure about what's happening with passive convention, I highly recommend that you draw a picture. And you may remember from our initial lecture, we saw in Lecture 1 that if we are flowing from high voltage to low voltage, and current is entering the positive end, or the higher voltage end, we can visualize our circuit component like a water wheel. And in the case of this first item, when passive convention is satisfied, we see that our water wheel will be spinning due to the current flowing through. Therefore, power is received or absorbed by the water wheel, or our circuit element. Similarly, we see that if our current enters the negative terminal, the water wheel will have to push the water up to the top of the hill, and therefore the water wheel would have to supply power. So, if needed, use pictures to help you visualize what's happening. All right, next item on our study guide is DC circuit analysis. So, throughout the first 10 lectures of our course, we have covered a great deal of tools to help us solve DC circuits. I highly recommend that you make an equation sheet containing all our DC tools. And in particular, make sure you have the following tools. So we have Kirchhoff's voltage law, Kirchhoff's current law. We have Ohm's law, series parallel resistors, how to simplify those. We have current and voltage division, node and mesh analysis, and general strategies for designing a circuit. And remember, we also covered in our later lectures the strategies for choosing which tool to use. So it might also be good to review our strategies for deciding which tool to use. Again, that was covered in lectures 7 to 8. So, quick review. So, again, I'm not going to have enough time to ask you to solve a really ugly system of equations during the exam. But I might ask you a question about writing node or mesh equations. So, you might want to review lectures 4 and 5. And you'll see in those videos, we demonstrated how to write the node equation by applying Kirchhoff's current law and writing in terms of voltage and resistance. And in lecture 5, we learned about applying Kirchhoff's voltage law to write a mesh equation in terms of currents. We have a few examples of this later, and I'd also encourage you to review lecture 4 and 5 if you need a refresher. Next item on our study guide is circuit theorems. So these are additional, very important tools that we use for DC circuit analysis. Make sure that you know how to find Thevenin resistance, Thevenin voltage, and Norton current. Remember, we covered these in lecture 7 to 8. And remember, if you're a professor who has to write an exam and you have limited time, it's convenient to write a question about Thevenin equivalence because you could also ask about techniques like node analysis, mesh analysis, voltage division, or even superposition and max power transfer. So if you need to test a student's understanding of many topics in a short exam, it's convenient to include a question on Thevenin and maximum power transfer because those questions also require other topics that we've learned. Let's briefly review the procedures for these circuit theorems. First, we covered source transformation. So make sure you remember how to use source transformation. Remember that we can replace a voltage source and series resistor by an equivalent current source and parallel resistor. Or we can do the reverse. To make this transformation work, we must use the equations shown here in order to replace with an equivalent current or voltage source and equivalent resistor. Also pay attention to the orientation of the source. Remember that the positive terminal of the voltage source and the direction that our current arrow is pointing, that needs to be kept consistent after the transformation is complete. Also remember, in order to do source transformation, our circuit elements must be linear, which is generally the case for our class. Also very important, please remember that our Thevenin and Norton theorems are related by a source transformation. So if you've found the Thevenin equivalent, you can use a source transformation to find your Norton equivalent. Also, I encourage you to review our Thevenin and Norton's theorems from lecture 7 and 8. So you'll remember we covered these procedures for solving Thevenin equivalent problems. Remember, the procedure is slightly different depending on whether you have dependent sources in your circuit. If you do not have dependent sources, then you can find Thevenin voltage as the open circuit voltage. And then you can directly determine Thevenin resistance. All you need to do is turn off your voltage and current sources, and then find your resistance when walking from terminal A to terminal B. And once you have determined your Thevenin voltage and Thevenin resistance, then you can replace the original circuit with that Thevenin equivalent. And if you want to find Norton, then you just do a source transformation. So once again, please do take a look at lecture 7 to 8 if you need a review on Thevenin's theorem. Be careful if you have a circuit with a dependent source, because the procedure for Thevenin's theorem and dependent sources is slightly different. So, if you have a dependent source, the Thevenin voltage procedure is the same. But notice if you are trying to find Thevenin resistance, that dependent source makes it a little more tricky. Remember that you have to attach an external source, VEX, with current IEX to your circuit. And then your goal is to find an expression for VEX over IEX in order to find our Thevenin resistance. So if you'd like more practice on this procedure, please do take a look at our previous videos. We also have an additional example that we'll do a little bit later. Finally, just a reminder about open and short circuits. So once again, remember an open circuit has no current flowing through it because it's a dead end. And a short circuit, by definition, has zero voltage across it. So if, for example, I have a resistor in parallel with a short, notice that no current will flow through that resistor because a short circuit has zero voltage across it. So if we have a resistor in parallel with a short, all our current is going to want to go through that zero voltage path because this whole area is sitting at the same voltage. And there is no voltage difference able to push current through that resistor. Remember, of course, that by definition, the voltage drop must be the same for components which are in parallel with each other. Also, if you have a resistor which is in series with an open circuit, so if we have some resistor here, notice that no current is going to flow through that resistor because that resistor is connected to an open. And remember, if the open circuit has zero current flowing through it, then by definition, current must be the same through all the components that are in series. So definitely watch out for open and short circuits, and make sure you can correctly recognize whether things are in series or parallel, and in series or parallel with opens and shorts. All right, our last circuits theorem here is our maximum power transfer theorem. If you see a question about maximum power transfer on the exam, you should immediately be happy, because that is free information. Remember, maximum power transfer theorem says that maximum power is transferred when the load's resistance equals the source's Thevenin's resistance. And so if that condition is satisfied, you'll remember that our maximum power that we're able to transfer is given by the maximum power transfer theorem equation here. So maximum power will be equal to our source Thevenin voltage squared divided by 4 RT. So if we know the Thevenin equivalent of a circuit, we can very conveniently determine the maximum power transfer capabilities of that circuit. Finally, our last circuit theorem that we covered is superposition. And remember, superposition says that in any linear circuit containing multiple independent sources, the current or voltage at any point in that linear circuit can be calculated as the algebraic sum of each source acting alone. So for example, in this figure, we see that our circuit with a voltage and current source can actually be rewritten as the sum of the current source alone plus our voltage source alone. And here we can say that VR4 total in our original circuit our total voltage across our component of interest is simply the algebraic sum of the voltage with each source considered separately. Notice this is algebraic sum, so you do need to keep negative signs and current and voltage directions in mind. Remember that the superposition procedure is actually pretty straightforward. And this is also a very convenient exam question because solving superposition problems often requires use of other tools like voltage division, node analysis, and our other DC circuit tools. So remember, what you want to do with superposition is draw the circuit with each source considered separately. And notice dependent sources are not changed. It is only for independent sources where you turn them off. Remember, to turn off the sources we don't want, voltage sources are replaced with a short or plain wire, and current sources are replaced with an open. Once you have drawn each source considered separately, then you calculate the contribution of each source alone to that desired parameter. Finally, you take the algebraic sum to determine the total of all contributions from all sources. We'll do an example of this a little later. And if you need an additional refresher, I'd encourage you to go back and review our superposition lecture. Last couple items on our study guide. First is amplifiers. Make sure you know the general terms, including the definitions and assumptions we make for ideal operational amplifiers. You should also know the golden rules and how to apply them. And finally, in lectures 9 and 10, we learned about standard operational amplifier circuits. So make sure you know how to use those standard op-amp circuits similar to the examples that we did. If I ask you to design a circuit that will do some sort of mathematical operation, you should be able to recognize which of those circuits we need in order to design that desired result. There might also be a few questions about kind of general amplifier theory and non-ideal amplifiers as covered in lecture 10. So remember, the golden rules of our ideal op-amps are pretty straightforward. So we assume the current going in to each input terminal is 0. And we also assume that the voltages of the two input terminals are equal. So here are the 6 standard op-amp configurations that we have covered. And remember, I do not expect you to memorize all these circuits, but I do expect that if I ask you to design a circuit that does some sort of mathematical operation, I expect that you would be able to select the correct circuit and tell me what resistor values you would need in order to design that circuit. All right, last items here. make sure you are comfortable with the topics we've covered in our labs. So that includes all the best practices about using multimeters and breadboards and assembling our circuits. And we also covered sensitivity analysis and Monte Carlo, so there might be some question about that. And you're not going to be required to do any sort of simulation during the exam, but you might need to identify errors or answer some questions about best practices in our lab skills. All right, so that concludes our review of the topics from our study guide. So in the last part of this video, we're going to go ahead and review some practice problems to help practice the topics on our study guide. Once again, I highly recommend that you follow along with me. Don't just sit and watch me solve these problems. Pretend it's the exam and see if you can solve them yourself. That's a really great way to practice and see where you might need to review more and see what topics you know well. So please feel free to pause the video and attempt these questions on your own. And remember, you can also skip around to the questions that you want to practice most. So let's go ahead and jump in to practice problems. Here's our first practice problem. Suppose we have 4 circuit elements. We have element A, B, C, and D. Question to you is, which of these elements supply 12 watts? Take a moment and see if you can identify the correct elements. All right, so let's go ahead and discuss. First, we want to remember our passive convention. If I want to be supplying power, current must be entering our negative terminal, and we must have a positive power value. So in this case, to supply, let's identify elements where we have current enters the negative terminal and power is positive. So notice choice A, that can't be supplying because we have current entering positive and positive power. Also choice D is absorbing. That leaves us choice B and choice C. And notice both of these will produce a power that is equal to 12 something, but watch your units. Notice here we have 6 volts times 2 milliamps, which gives us 12 milliwatts. So notice choice C, it is supplying, but it's only supplying 12 milliwatts, so correct answer here is our choice B. Choice B is supplying 12 watts to our circuit. Let's move on to practice number 2. This is a practice on node analysis. We are told node 1 has an unknown voltage V1, and we want to write the node equation for node 1. Let's remind ourselves of our procedure for node analysis. Remember, first, we need to apply Kirchhoff's current law to the node. So if needed, draw in reference currents. Also, if needed, you want to assign a ground node if not given. So here we are already given that our bottom node is 0 volts. So here we were already given to use that bottom node for our reference, but if that was not given, you would have wanted to assume a ground node. So once we've applied Kirchhoff's current law, then we need to rewrite our Kirchhoff's current law equation in terms of the node voltages and resistances. Here we are just looking for the node equation, so we can go ahead and stop after that step, but of course, if you are trying to solve, then you could solve the node equations to find the node voltages. So in this case, we don't need to do step 3. We'll just do steps 1 and 2. So they did not tell us what direction our currents were flowing, so I'm just going to assume some directions. So I'm going to assume I have I1 flowing from my 3-volt source into V1. I'm going to assume I have I2 flowing from that current source into V1. And I'm going to assume I have current I3 flowing from my voltage source V1 down into the ground. Remember, it does not matter which way you draw your arrows as long as you hold a consistent sign convention. So for step 1, I can apply Kirchhoff's current law, and I determine that I have plus I1 entering my node, plus I2 also entering V1, then minus I3, because I3 is leaving my node. And so those 3 currents must sum to 0 by Kirchhoff's current law. If you need a review on this, check out lecture 4 for a review about how to do this procedure. Our next step is to rewrite these currents I1, I2, and I3 in terms of node voltages. So in this case, notice for I1, we're sitting over here at 3 volts initially, and then we end at V1. We pass through a 2 ohm resistor. So I can write that my current I1 is just 3 volts minus V1 volts divided by 2 ohms. Just using Ohm's law and the voltage difference from my higher point 3 volts to my lower point V1. Remember, because I drew my arrow flowing from the 3-volt source to V1, I am inherently assuming that 3 volts is the higher voltage, so I must subtract V1 from 3 volts. You can also draw a picture if you need help, just visualizing what's happening here. What about I2? Well, it turns out we know I2. We are given this 2 milliamp source, so because that's just flowing through a resistor, there's no other paths for that current to go. We know that I2 must be equal to 2 milliamps, because that's the only path that current can take from the 2 milliamp source into V1. And I can proactively convert my units to amps so that I don't screw up later. Finally, my current I3. Well, initially I'm sitting at voltage V1. Then I end at 0 volts after passing through that 4 ohm resistor. So I can write my current I3 as V1 minus 0 over 4. Now I can substitute those currents into my Kirchhoff's current law equation, and I determine my final node equation. The equation is 3 minus V1 over 2 minus 0.002. Whoops, be careful of signs. Actually here, remember, it's plus I1, so we have plus that current, so plus 3 minus V1 over 2, plus I2, because I2 is coming in, so we have plus 0.002 amps. And then finally, I3 is leaving, so we say minus V1 over 4 equals 0. And there is our node equation for node V1. In this case, I have just one equation, one unknown, so if I needed to, I could go ahead and solve that equation for V1 directly. Here, since I was just asked to write the node equation, I'm going to go ahead and leave that equation as is. All right, let's move on to the next practice. In this example, we are asked to write a node equation for the supernode, then determine VA. You'll remember we covered our supernodes in Lecture 4, and also a little bit in Lecture 5. So you'll remember that a supernode is a voltage source between two nodes. Supernodes are a special case of node analysis. So in this case, I can go ahead and let's just assume that my bottom node is ground. And hey, what do you know? I just have one voltage source in this circuit, and it is indeed sitting between two distinct nodes. And you'll remember, if you run into a supernode in your circuit, the strategy that you want to follow is to apply Kirchhoff's current law to the supernode. And so you treat the whole supernode as a larger node with the algebraic sum of the currents entering and leaving being 0. And notice you can also use the relationship between the voltage source and the two nodes to get a second equation. So in this case, notice that initially my bottom node is sitting at 0 volts or ground, but I'm told that I want to find VA across that 100 ohm resistor. So in this case, I can conclude that my voltage on the right-hand side of my 9 volt source, that voltage must be VA. And then if I draw a picture, notice that if I were to walk across this source, I'm going to be 9 volts higher on the left-hand side of my source. Therefore, on the left-hand side of my source, I must be sitting at a voltage of VA plus 9. So basically, by using this voltage source, I can find some relationship between those two nodes. And so that can help me solve my problem. So let's go ahead and try this. Our first step is to write a node equation for that supernode. Then we want to find VA. So to write our node equation, we need to first apply Kirchhoff's current law, and then rewrite in terms of our node voltages. So here I'm just going to assume some currents. I'm going to assume I have current I1, I2, and I3. Notice I1 and I2 are kind of leaving from that VA plus 9 point. I3 is the current flowing from VA down to 0 volts. So if I apply Kirchhoff's current law with those currents, I determine that I have minus I1, minus I2, minus I3, and everybody sums to 0. Next, I need to rewrite those currents in terms of my node voltages. So in this case, notice for current I1, I am flowing from VA plus 9 down to 0 volts. I pass through a 250 ohm resistor. So in this case, I can say that my current I1 is VA plus 9 minus 0 over 250. Notice my current I2 is actually, in this case, given by that ideal current source. So I can just say my current I2, it has to be 0.02 amps because that current is flowing through that part of the circuit. Finally, my current I3, well, I start at my voltage VA, I flow through a 100 ohm resistor, I end at 0 volts. So that means my current must be VA minus 0 divided by 100. So if I substitute these back into Kirchhoff's current law, I get my node equation for that supernode. So we end up, again, be careful of negative signs here. We get negative VA plus 9 over 250 minus 0.02 minus VA over 100 equals 0. So we finished the first part. We have successfully determined that node equation. Now we need to solve for our voltage VA. So let's solve our supernode equation for VA. So here's what we had. So from our supernode equation, we determine this is our relationship. And I'm going to just go ahead and multiply everybody by 500. And if I do that, then again, just be careful of negative signs. We get essentially everything in the numerator of that first term is multiplied by 2. So I get negative 2 VA minus 18. 0.02 times 500 will give us negative 10 here. And then VA over 100 times 500, that will give us minus 5 VA. And so we have that. If we combine terms, we get minus 7 VA equals 28. And that means that VA must be equal to negative 4 volts. So notice how drawing pictures and correctly applying node analysis and our tools we've learned is really important for solving supernodes. Okay, let's move on to our next practice. In this practice, we want to draw a mesh equation for the loop containing our current I2. So in this case, when we want to write a mesh equation, that means first we need to apply Kirchhoff's voltage law, and then we need to rewrite Kirchhoff's voltage law in terms of our mesh currents. So let's go ahead and do that. And you might find it helpful to review Lecture 5 for this procedure. I'm going to go ahead and start in the bottom left corner of my circuit and walk clockwise around. And as I do that, I'm going to apply the bank account convention. This is a great use of our tools from Lecture 5. So if we walk around our circuit, we first see our 200 ohm resistor. So I'm going to experience 200 ohm resistor voltage drop. I walk from negative to positive of the 2 volt source, so that means I'm going to gain 2 volts by my convention. Then I walk across a 300, 100, and 100 ohm resistor, so I'm going to go ahead and walk across all of those. And notice that I'm keeping my 100 ohm resistors as separate terms because they do overlap with different meshes in that circuit. So that's my Kirchhoff's voltage law equation. Now I need to rewrite that in terms of my mesh currents. I know for the voltage drop across my 200 ohm resistor, I only have current I2 flowing through that point. So I know that voltage is going to be 200 I2. Similarly, only I2 is flowing through our 300 ohm resistor, so that voltage will be given by 300 I2. Be careful with these 100 ohm resistors though. Notice that I have current I2 flowing in the direction I'm walking, but I also have current I3 flowing opposite. As we learned in our video, that means our voltage drop here will be resistance times the net current through that resistor, which will be I2 going in the direction we want, minus I3 opposing us. And finally, our last voltage, by the similar reasoning, will be 100 times I2 minus I1 because we have I1 opposing us and we're heading in the direction of I2. So finally, if we substitute everybody, paying attention to negative signs, we end up with negative 200 I2 plus 2 volts minus 300 I2 minus 100 times I2 minus I3 minus 100 times I2 minus I1 equals 0. So notice if I'm asking you just for the mesh equation, you can go ahead and leave it in this form exactly. You don't need to simplify this equation further unless I had asked you to actually solve for those currents. All right, so our next practice involves using a supermesh. So in this circuit, we are being asked to find the current IA in this circuit. Notice IA is actually the current going through our 20 ohm resistor. And notice there's also a dependent current source that depends on 5IA. And as hinted in this question, a good strategy is to use a supermesh. Remember, a supermesh is a special case of mesh analysis when we have a shared current source. So in this case, notice we can apply a supermesh equation around that diamond-shaped portion, and that will allow us to get one equation for our circuit. And we also have several nodes, which I will just label here as node 1, node 2, and node 3. So one strategy is to write a supermesh equation and then use Kirchhoff's current law at our nodes to determine the current through each resistor. In terms of IA. And then finally, we can substitute into our supermesh equation and solve for our IA. Let's go ahead and give this a try. So I'm going to write my supermesh equation starting by walking around my circuit in the clockwise direction. And I'm going to use the convention that the voltage across a resistor in the direction I'm walking will be a negative value. So if I apply Kirchhoff's voltage law, I'm going to determine that the voltage drop across my 15 ohm resistor plus the voltage drop across my 5 ohm resistor, and here I'm treating it as a negative sign because I am losing voltage to go through that resistor, minus V10, or the voltage across my 10 ohm resistor, minus V20. I'm going to take algebraic sum of all those voltages to be 0 within my closed loop. So again, this must be true by Kirchhoff's voltage law. And then we also know by Ohm's law voltage must be current times resistance. So we can write that minus 15 ohms for a 15 ohm resistor times I15 minus 5 ohms times I5 minus 10 ohms times I10 minus 20 ohms times I20 must be 0. So here I'm just assuming I have some currents flowing through each resistor. So one thing you want to be careful here is you want to recognize that I10, for example, is not going to be equal to IA because there are branches and multiple paths for the current to take. So we need to apply Kirchhoff's current law at each node. to determine expressions for each current. And I'll just number these once again as node 1, node 2, and node 3. Let's look at node 1 first. In node 1, I have 5IA entering. I have IA also entering. And I know I must have I15, the current through my 15 ohm resistor. That current must be leaving. So I can conclude, by Kirchhoff's current law, I can say that plus 5IA plus IA minus I15 equals 0. If I solve for I15, I determine that I15, that's the current through my 15 ohm resistor, that must be equal to 6IA. Let's look at node 2. Notice entering node 2 from below, I have I15, which I found to be 6IA. I have 2 amps entering from the right due to my independent source. And I have I5 exiting and entering that 5 ohm resistor. So by Kirchhoff's current law, I can conclude that plus 6IA plus 2 amps, minus I5 must be 0. Solving for I5, I determine that the current through my 5 ohm resistor must be 6IA plus 2 amps. Finally, let's look at node 3. So looking at node 3, I conclude I have current I5 entering, where I5 is equal to 6IA plus 2. I also have 5IA leaving from that dependent source, and I have I10 leaving and going through the 10 ohm resistor. By Kirchhoff's current law, I can say I have plus 6IA plus 2 entering, minus 5IA leaving, minus I10 leaving. If I solve for I10, I determine that the current through my 10 ohm resistor must be equal to I sub A plus 2. And finally, by looking at the 20 ohm resistor, I can conclude that I20 must be equal to I sub A. So notice what I can do here. I can substitute each of these currents into my supermesh equation, and I will have one equation and one unknown, which I can solve for I sub A. So I can substitute each current into the supermesh. And then once I substitute, I can solve for I sub A. If I do that, we will get the following. We will get minus 15 times the current through our 15 ohm resistor, which is just 6IA. Then we have minus 5 ohms times I5, which is 6IA plus 2. Then we have minus 10 times the current through our 10 ohm resistor, which is IA plus 2. And then finally, we have minus 20 times I sub A, which is the current through our 20 ohm resistor. So in this case, we get negative 90 I sub A, minus 30 I sub A, minus 10 I sub A, minus 20 I sub A equals 0. If we combine like terms, we have negative 90 minus 30 is negative 120, minus 10, which is minus 130, minus 20, which is minus 150 I sub A, minus 10 minus 20, which gives us minus 30 equals 0. So we determine I sub A is equal to, in this case, will be negative 30 over 150, or 315 amps. And don't forget that negative sign. Remember the negative I sub A, that just tells us that our current I sub A is actually going in the opposite direction as we had drawn in our supermesh. So there you have it. This is a great practice of using Kirchhoff's current law and Kirchhoff's voltage law to solve a circuit. All right, our next practice is superposition. And in this case, we want to use superposition to find the voltage V0 across that 30 ohm resistor. I'd encourage you to pause the video and give this one a try on your own, and then we'll go ahead and do it together. So you'll recall the first step of superposition is to draw the circuits with each source considered separately. So in this case, if we do that, we get the following. With our 10-volt source alone, I'll go ahead and I'm going to call this, in this case, V02. And I'm going to say, here's my 30 ohm resistor, 120 ohm, 96 ohm, and 32 ohm. So notice with the voltage alone, my current source gets replaced with an open. And then similarly, I can draw the circuit with no voltage source. Remember, the voltage source is replaced with a short or a plain wire. I'm going to call this V01. And we have our 0.2 amp source all by itself in that second circuit. By superposition, we can say that our total voltage V0 is going to be equal to V01 plus V02. So we need to use our DC circuit tools that we already know to solve for those two voltages. So the one other thing you want to be careful here is pay attention to polarity. Let's look at V02 first. Notice for circuit V02, we can consider this upper portion of our circuit by Kirchhoff's voltage law to be two resistors in series with that 10-volt source. By Kirchhoff's voltage law, we know that the 30 ohm resistor and the 120 ohm resistor must experience a voltage change of 10 volts. So I can actually consider that piece of my circuit all by itself. So if I have a circuit like this with two series resistors, and I want to find the voltage across one of them, what could I do? Well, in this case, we can either use Ohm's law or we can do voltage division. The thing you want to watch out for with voltage division is that if I'm solving for voltage with voltage division, I'm actually going to be finding the reverse of the voltage that I want due to polarity. When using voltage division, I'm assuming current is flowing from the positive terminal of my voltage source to the negative. So the voltage given by our voltage division will be equal to negative V02 because the polarity is opposite. So be careful there. If you run into a question where you're using voltage division, make sure that you calculate your final voltage in the polarity that you want. So here I'm going to say voltage across my 30 ohm resistor. That's the same thing as negative 1 times the voltage I want. By voltage division, that voltage drop is going to be 30 ohms divided by 30 plus 120. Basically the sum of my two series resistors, times Vs, our source voltage, which is 10 volts. So in this case, I determine that my negative V02, the voltage I want to find, is just 30 over 150 times 10. Or if I math that through, it's 2 volts, so that gives me V02 is negative 2 volts. So polarity is very important there. Please pay attention to that polarity. So we found V02. Let's find V01 next. So notice that because we have a short on this circuit, if I were to walk through this circuit, I see that I have two sets of parallel resistors. So I could actually redraw this circuit like this. So I have my 30 ohm resistor and my 120 ohm. Remember, my voltage is basically the voltage across that set of parallel resistors. And then I have my 96 ohm and my 32 ohm resistor in parallel with each other. I can further simplify this circuit if I use our formula to simplify those parallel resistors. But notice I don't want to combine my resistors fully because I want to determine V01. I'll determine that in this case I basically have two 24 ohm resistors in series with each other. So if I go ahead and find V01, all I need to do is consider I have 0.2 amps of current through a 24 ohm resistor. So therefore, by Ohm's law, V01 is equal to 0.2 amps times 24 ohms, which is equal to 4.8 volts. So remember, by superposition, the total voltage across that 30 ohm resistor is going to be the algebraic sum of the two. So in this case, I can determine that V0 total is equal to negative 2 volts plus 4.8 volts. So that gives me final answer of V0 is equal to 2.8 volts. So there you have it. Make sure you pay attention to polarity and draw lots of pictures when doing these superposition questions. It's very important to draw each circuit correctly so that you can correctly determine the desired parameter with each source alone. Our next example is source transformation. Here we want to determine Vs and Rs so that the two circuits are equivalent. So here you'll want to remember our superposition rules that we covered in our lecture 6. And so in this case, we know that Vs must be equal to Rp/Ip, where Ip is our parallel resistor, or Ip is our parallel current source, Rs is our parallel resistor, and we know that Rp and Rs must be equal. Notice the orientation of our sources. Notice that in source transformation, we need to keep the source orientation constant. So we could redraw our circuit B as having our current source going in the upward direction. But notice our current, if we flip the direction, this will be a negative 2 amp upward current. So make sure you keep the source orientation constant here. Since we are looking for Vs with its positive polarity upward, we need to plug in our current source, Ip, with its current pointing upward. So in that case, Ip is negative 2 amps. So pay attention to the sign. Knowing that Ip is negative 2 amps and Rp is 10 ohms, we can use our equations to determine the equivalent. So if we plug everybody in, we determine Vs is equal to our 10 ohm Rp times negative 2 amps Ip, which is negative 20 volts. And our series resistor Rs is just going to be the same as Rp, which is 10 ohms. So overall, source transformation is pretty straightforward, but be careful to keep the source orientation constant and watch out for possible sign errors if the orientation of your sources is reversed. Also, pay attention to units. Remember, you want to be working with volts, ohms, and amps. So if you have some other type of unit, make sure you convert accordingly. All right, our next example is finding the Thevenin equivalent of a circuit with a dependent source. In this case, we want to find the Thevenin equivalent of this circuit connected to our load. So essentially, we can remove our load and just consider the portion of the circuit connected to that load. Let's go ahead and give this a try following our Thevenin procedures. And remember, if you need a refresher, you can also take a look at lecture 7 and 8 for the full Thevenin explanation. Okay, so let's first start by finding our Thevenin voltage. And remember, that is the same as VOC, our open circuit voltage. I'm going to go ahead and disconnect our load and draw the circuit with only the portion we care about. So we have this. And our goal is to find VOC. Remember, VOC is basically the voltage across this terminal A to terminal B. If I let the bottom portion of my circuit be sitting at ground or 0 volts, I can determine that VOC must be the upper right node. So our task is to find VOC. And this might seem a little tricky at first. But let's think about what we know. Well, we happen to know that the node on the left here is sitting at VA less, or I'm sorry, VA higher because of the polarity. So over here, this node must be sitting at VOC plus VA volts. And we also have a dependent source which depends on voltage VA across our 3 ohm resistor. So that's what we know. And so if we look here, we have 2 nodes. We also have 2 meshes. There's not a lot that we could do source transformation on. But a good approach we could use here is using node analysis and Kirchhoff's voltage law. Let's first start with Kirchhoff's voltage law. We know the voltage across that 4 amp current source must be the same as VOC because that's just the voltage between point A and point B. So by Kirchhoff's voltage law, we can write that plus VOC, if I go walking in the counterclockwise direction, I can say plus VOC plus VA minus 1.5 VA equals 0. So this is just walking in a counterclockwise. So notice I determine, in this case, VOC minus 0.5 VA equals 0. So that gives us VOC is equal to 0.5 VA, or I could write that VA is equal to 2 VOC. So I need another equation for my voltage VOC in terms of VA. Let's try node analysis to get a second equation. In particular, I'm going to use node analysis at the node VOC to get a second equation. All right, so I don't know for sure which direction the current's flowing, but I'm going to assume I have some current I1 that enters VOC from left to right. And I'm going to assume I have a second current I2, which is entering VOC from below. Since node A is currently connected to an open, I'm not going to consider any current through there. by definition, an open has zero current. So by Kirchhoff's current law, I can write that plus I1 plus I2, algebraic sum of the currents entering node VOC, that must be zero. And what else do I know? Well, I know that I2 is just going to be 4 amps because I've got a current source there. And notice for current I1, that's the current through my 3 ohm resistor. I know I have VA volts across that, and I can also write that I have 1.5 VA on the left-hand side of that 3 ohm resistor, and I have VOC volts on the right-hand side. Again, that just comes from my figure. So I can determine in this case that if I want to find my current that is flowing through that 3 ohm resistor from 1.5 VA to VOC, I can write that my current I1 is just going to be 1.5 VA minus VOC divided by 3 ohms. So notice I can substitute into this Kirchhoff's current law equation, and I'll determine if I substitute both those terms, I have 1.5 VA minus VOC divided by 3 plus 4 equals 0. From earlier, I know that I can write that VA is equal to 2 VOC. So I can also substitute that. And if I do that, then I determine 1.5 times 2 VOC minus VOC divided by 3 plus 4 equals 0. I have one equation, one unknown. I can solve this for VOC. Let's go ahead and do that real quick. We multiply both sides by 3. We get that. And so I get 3 VOC minus VOC equals negative 12. 2 VOC is negative 12. So I get VOC is negative 6 volts. That means that my Thevenin voltage is negative 6 volts. So that's the first part of our Thevenin equivalent. I found Thevenin voltage, but I need to also find our Thevenin resistance. So let's find Thevenin resistance next. So following our procedure from lecture 7, notice we have a dependent source in this circuit. So we need to follow the Thevenin resistance procedure for dependent sources. So first we need to turn off our independent sources. So our 4 amp current source becomes an open. Then we need to connect an external source, VEX, with current IEX, and then we need to solve for an expression relating VEX over IEX. That will give us our Thevenin resistance. So let's draw our circuit with these new conditions. I'm going to replace my dependent voltage VA with voltage VA prime, just to avoid confusion, because since I'm turning off that current source, my voltage VA is going to be different. Notice my current source becomes an open, but I still have my 2 ohm and 3 ohm resistors in there. Still have my dependent source. And I now have connected my external source VEX with current IEX. Remember, we want to find Thevenin resistance by dividing VEX over IEX. Let's start by getting some expressions that relate VEX and IEX. A good place to start is that 3 ohm resistor. So let's first write an equation for IEX through our 3 ohm resistor. So here, we know we have VEX volts on the right-hand side. If we let our bottom node be ground, then we can assume that our voltage to the left of our 3 ohm resistor is just 1.5 VA prime. So in this case, we can go ahead and write the following. We know that IEX must be equal to our voltage VEX minus 1.5 VA prime divided by our 3 ohm resistor. Notice we need a second equation here. We need some second equation specifically relating VEX and VA prime. What else do we know? Well, I want a convenient way to relate VEX and VA prime, so how about applying Kirchhoff's voltage law? If I walk around the entire perimeter of this circuit, I can determine that plus 1.5 VA prime minus VA prime, that's the voltage across my 3 ohm resistor, minus VEX, all that must sum to 0. So in this case, I can determine, if I combine terms, I see that 0.5 VA prime minus VEX must be 0. So in this case, I can see that VA prime must actually equal to VEX. Well, that's convenient, because now I can take that expression and plug it into what we had before. So let's go ahead and substitute. And if we do that, we can determine that IEX is going to be VEX minus 1.5 times 2 VEX divided by 3. So solving for VEX over IEX, we get 3 IEX is equal to VEX minus 3 VEX. So therefore, we get minus 2 VEX equals 3 IEX, or VEX over IEX is equal to negative 3/2, or negative 1.5 ohms. That means our Thevenin resistance is negative 1.5 ohms. Remember that the Thevenin resistance is a model that represents an equivalent circuit. So it is possible to get negative Thevenin resistances when you have a Thevenin equivalent with a dependent source. So don't panic if you see a negative Thevenin resistance. As long as you have followed the procedures correctly and not made any sign errors, then it still can be the correct equivalent resistance. So I definitely encourage you to try this example on your own and verify that you can get the same result. And remember, if you'd like additional practice, I highly recommend you check out our Lecture 7 and 8 videos. Let's now finish with our last practice question. This question has to do with maximum power transfer theorem. Here we are told we are using a 12-volt car battery to charge our phone. And in the first part, we're told if it takes 30 minutes to charge our phone, and our phone has a battery capacity of 60 kilojoules, determine the power being delivered by the battery, by the car battery, that is, to your phone battery. So we may assume that the entire 60 kilojoules needed to fill our phone battery, those are delivered in 30 minutes. Second part of the question asks us to determine the resistance of our phone battery in ohms, and finally, how much charge is delivered to our phone in coulombs during that charging period. So let's start with the first part of the question. And I encourage you to try pausing the video and attempting this on your own first. So the key thing to remember for our first question is remember how power and energy are related. So remember, 1 watt is equal to 1 joule per second, or energy, W, is the integral of power. So in this case, we know that in 30 minutes, we are able to deliver 60 kilojoules, or 60,000 joules. So we can convert units and determine how many joules per second am I delivering if I have 60,000 joules transferred in 30 minutes. If I convert to joules per second, that will give me my power in watts. So in this case, I have 60,000 joules per 30 minutes, and I know that in every 1 minute, there are 60 seconds. So if I do a short unit conversion, I can determine that I have 33.33 joules per second. That means my power is equal to 33.33 watts. So I'm not going to really bother too much with significant digits or anything at this point. I'm just calculating my power here. Let's move on to the next part of the question. Next part of the question says we discover that the resistance of our car battery and phone are matched and maximum power transfer is satisfied. So we are asked to determine the resistance of our phone battery in ohms. That's the resistance of our load. So we are told that maximum power transfer is satisfied. That means that our load resistance is equal to the source resistance here. And that also means that the power we're transferring is equal to our source voltage Vs over 4 RT, where again, RT is the Thevenin equivalent of our source circuit, or Thevenin resistance of our source circuit. Oops, I'm sorry, I forgot the squared. Remember, by maximum power transfer, our maximum power will be Vs squared over 4RT. Well, would you look at that? We just determined that we're transferring 33.33 watts, and we know our voltage source is 12 volts, so we can just solve for our Thevenin resistance. And we determine in this case, if we go ahead, plug everybody in, we'll determine solve for RT, we get RT, which is equal to our battery. That will be equal to 1.08 ohms. So this part is now complete. Last part of the question is asking how much charge is delivered during that charging period. So how much charge did we deliver in 30 minutes or 1800 seconds, right? Well, what do we know? Well, if we want to find charge, remember, charge per time is current. So we need to find our current. And in this case, we know power is equal to IV or I squared R, so why not use the resistance of our battery and the power we know? If we substitute into P equals I squared R, we'll determine that 33.33 watts must equal I squared times our resistance. And in this case, let's make sure we plug in the correct resistance here. So we know, in this case, the resistance of our load is going to be equal to that 1.08 ohms. And so therefore, we need to go ahead and solve for I. And if we do that, we will get the following. We'll determine that I squared is equal to 30.86, that's just 1.08. And again, divide our power by that 1.08. And then we need to take the square root of that 30.86. And if we do that, we determine our current I will be equal to about 5.555 amps. And then lastly, that's our current. Remember, that is coulombs per second. And we were delivering that current for 1800 seconds. So remember, charge is the time integral of current, or current times time. So therefore, our charge Q in coulombs is going to be equal to our current, which is 5.55 amperes times 1800 seconds, or 30 minutes. And if we solve for that, we get about 10,000 coulombs. So there you have it. So be careful once again. Make sure that you pay attention to units. Common mistake is to accidentally mix up your seconds and minutes, and draw pictures to keep track of which resistor and which part of the circuit you're looking at. So this concludes our review for Exam 1, so I hope you found these practice problems helpful. Definitely go back through them on your own, and additional examples as needed until you get comfortable with these concepts. And feel free to reach out if you have any other questions. Thanks, everyone, and we'll see you in the next video.